If you remember, we discussed the magnetism on the atomic level, on the electronic level. We said that the magnetism associated with the spin and orbital motion of an electron. Now let us turn to an atom. So in an atom, you know that there are several electrons, and then the magnetism of any one of these electrons interact with the magnetism of the other electrons. So we will have to understand this interaction and this coupling of magnetism from one electron to another electron. And our today's lecture concerns the same thing. So you must go to page number 428 of the book we are discussing, and we have at this page, let us start from this paragraph. It is useful to establish a correspondence between the classical and quantum descriptions of the dipole motion in a magnetic field. Note that for the orbital case, the energy splitting delta E is equal to mu B into B, and this is also equal to H omega L, H cut omega L, where omega L is the Larmor frequency given by equation 9.10. Thus, the quantum frequency for the transition between the Zeeman levels is equal to the classical Larmor frequency. The same correspondence applies to spin, where both the Larmor frequency and the Zeeman splitting are twice as large. So up till now, we have considered the orbital and spin angular momenta separately, but as I told you before, when an electron has both types of momenta, as frequently happens, there is an interaction between them, and the two should be treated simultaneously. So this situation and its bearing on magnetism will be discussed next in section 9.6. So here is this section 9. That we will discuss in section 9.6 later. But let me introduce the other magnetic parameters here, which are very important. For example, we have magnetic susceptibility. Now, the magnetic field can be described by either of the two vectors, the magnetic induction B or the magnetic field intensity H, which are related in vacuum by the formula B is equal to mu naught H, where mu naught is 4 pi into 10 to the power minus 7 Hertz per meter, and is called the permeability of free space. So you must not confuse mu m with mu naught. Mu naught here is being represented to show the permeability of free space. and mu m is the magnetic Bohr magneton. So when a material medium is placed in a magnetic field, the medium is magnetized. This magnetization is described by the magnetization vector m, the dipole moment per unit volume. So m is the dipole moment per unit volume of the solid. The magnetic induction inside the medium is then given by the relation mu is equal to mu naught h plus mu naught m using equation 9.16. Okay, and this equation 9.17 you should recall from basic physics. The induction is composed of two parts, the part mu naught h generated by the external sources and the part mu naught m due to the magnetization of the medium. Since the magnetization is induced by the field, we may assume that m is proportional to h. That is, the m is equal to mu h, chi h. This chi is the proportionality constant here, and this is another magnetic parameter which we are going to define. This is known as the magnetic susceptibility of the medium. Okay. When this expression for m is inserted in equation 9.17, it leads to b is equal to mu naught bracket 1 plus chi into h. Thus the vectors b and h are proportional to each other by the formula that b is equal to mu h, and the proportionality constant mu is given by mu naught into 1 plus chi, and this proportionality constant mu is known as the permeability of the medium. So this is yet another magnetic parameter associated with the magnetism of a solid. It is often more convenient to use the relative permeability denoted by mu r, which is defined as mu r is equal to mu over mu naught, a ratio of the permeability of that medium to the permeability of free space, and therefore mu r, comparing this with equation 9.21, comes out to be 1 plus chi. Now this is a very useful relation which connects the permeability and susceptibility of the medium. That is, which connects the latest magnetic parameters we have defined. Okay, let's go to the next page. So our approach here clearly parallels that was used in the dielectric case. Note, however, that in writing equation 9.18, we assume that m is as demagnetization field, local field, corrections, etc., which we felt obliged to include in the electric case. The neglect of these factors is justifiable in the magnetic case because m is very small compared to h. Typically, chi is of the order of 10 to the power minus 5. So that's why we will not consider the demagnetization field and the local field. Okay, unlike the electric case in which chi is quite considerable. In the electric case we saw that chi is of the order of 1, but here chi is of the order of 10 to the power minus 5. So less. So when we deal with ferroelectric materials, however, where m is quite large, this omission is no longer tenable, and the above effects must be included, as we shall see in that section. Okay, now let us classify our materials with reference to magnetism. Materials may be grouped into 3 magnetic classes depending on the sign and magnitude of susceptibility. Now, those materials for which chi is positive, that is, for which m is parallel to h, they are known as paramagnetic substances or solids, whereas those for which chi is negative, that is, for which magnetization is opposite to h, they will be called diamagnetic. Now you can have a look on table 9.5 here, which gives susceptibilities for some representative substances and emphasizes once more the smallness of the magnitude of chi. So here, for example, for aluminum, which is a paramagnetic material, chi is plus 2.2 into 10 to the power minus 5. That is, chi is positive, however its magnitude is very small. Similarly, manganese and tungsten, they are paramagnetic substances, whereas copper, gold, silver, water and hydrogen, the magnetic susceptibility is not only low in magnitude but is negative as well. So these materials are obviously diamagnetic, and we have yet another class known as ferromagnetic, which we will discuss later. Okay, paramagnetic materials, the best known examples of paramagnetic materials are the ions of transition and rare earth ions. The fact that these ions have incomplete atomic shells is what is responsible for their paramagnetic behavior. So we see that in paramagnetic materials there are unpaired electrons in the atomic shells, and whereas in diamagnetic materials the electrons are paired up, and the magnetism of one electron is being cancelled by the magnetism of the other electron because of opposite spin. So diamagnetic materials, ionic and covalent crystals are diamagnetic. These substances have atoms of ions with complete shells, and their diamagnetic behavior is due to the fact that a magnetic field acts to distort the orbital motion. Now, this is the third type of magnetic materials known as the ferromagnetic material. Now, the magnetic susceptibility for ferromagnetic material is very large. It is 10 to the power plus 5 per cubic centimeter, unlike the paramagnetic, in which the magnetic susceptibility was in the range of 10 to the power minus 5. But here it is 10 to the power plus 5. Very high value. That's why these substances are called ferromagnetic substances, and they become spontaneously magnetized below a below a certain temperature. Examples are the ferromagnetic metals, iron, cobalt, and nickel, and their alloys. We shall discuss them and enumerate some of the interesting phenomena they display later in this chapter. Okay, let us now first take up the diamagnetic substances and discuss their magnetism. Now, Langevin was the scientist who discussed and analyzed these substances, and he came up with an equation which we will call Langevin diamagnetic equation. So let us now discuss Langevin diamagnetism. Now, what is a diamagnetism? It is associated with the tendency of electrical charges partially to shield the interior of a body from the applied magnetic field. Okay, in the atom, you know that there are the outer electrons in the outermost shells, and then there are the inner electrons. Now, what is diamagnetism? It has been introduced by the tendency of electrical charges partially to shield the interior of a body from the applied magnetic field. Let us now establish the fact that effect of a magnetic field on the orbital motion of an electron is such as to produce a diamagnetic susceptibility. Consider an electron rotating about the nucleus in a circular orbit, and let a magnetic field be applied perpendicular to the plane of this paper as shown in figure 9.6a. This is the figure 9.6a. So we have the field coming out of the paper, electron moving in the counterclockwise direction and around the nucleus. So this electron will experience two types of forces. One is the Coulomb attractive force towards the nucleus, and this force is represented by the arrow towards the nucleus, written as F0, and the other force is the Lorentz force, that is the interaction of this electron with the externally applied field B. So let us take up the equations. We know that according to Newton's law, the electrical attractive force between the nucleus and the electron is equal to m omega naught square r. This equation is the same as I have handwritten on the right side of equation 9.23, that is mv square over r, which is the centripetal force, and by substituting v is equal to r omega, you get this equation, that F0 is equal to m omega naught square into r. where F naught is the attractive Coulomb force between the nucleus and the electron, and omega naught is the angular velocity. So the magnetic moment of the electron, as we defined before, is equal to current I into the area of this loop. So let us substitute current equal to E omega naught over 2 pi and area is equal to pi r square to get equation 9.24, that mu naught is equal to E over 2 omega naught r square, where r is the radius of the electron's orbit. This moment is parallel to the field for the geometry and sense of rotation shown in this figure. So this is the figure which I have already illustrated. Okay. Moving on to the next page, we have the angular velocity is now different from omega naught, and its value may be determined from this relation. Now the solution of this quadratic equation in omega, which quadratic equation? Okay, this quadratic equation. Let me go back and show you. This is the quadratic equation, that F naught minus EB into RW is equal to M omega square R. Okay, now in this quadratic equation in omega is being solved mathematically to write that omega is equal to omega naught minus EB over 2M, and omega naught was the angular velocity of the revolving electron in the absence of the field. So when the field is applied and we get the factor EB over 2M, then the new angular velocity is omega is equal to omega naught minus EB over 2M, and the difference between this new angular velocity and the angular velocity before omega naught, that is omega minus omega naught, written as delta omega, is obviously equal to minus EB over 2M. Okay, this equation represents what is known as Larmor theorem. So this is the mathematical equation of Larmor's theorem, and if you are interested to see the statement of this theorem, then you must refer to page 436 in the book Solid State Physics by Kittel at page 5th edition, which shows that the rotation of the electron has been slowed down. So because of this negative sign, our change is negative, which means the angular velocity has been reduced by this factor on the introduction of the external magnetic field. So we can say that the rotation of the electron is being slowed down. This reduction in frequency produces a corresponding change in the magnetic moment, which according to equation 9.24 is equal to delta mu equal to minus bracket E square R square over 4M into the magnetic field B. the right side I have illustrated the derivation of this equation, equation 9.27. So since the moment parallel to the field has been reduced, this is a very important sentence, since the moment parallel to the field has been reduced, the induced moment is opposite to the field, that is, the response of the electron is diamagnetic. What is I'm saying? That as soon as we apply the magnetic field, external magnetic field B, and the motion of the electron is slowed down, and we can say that the response of the electron is diamagnetic because magnetism is being reduced. So that's why we have used the word diamagnetic. So the response of the electron to the externally applied field, magnetic field, is diamagnetic, and this is the inherent property of the electron. So it can be readily appreciated that if we initially choose an electron which was rotating counterclockwise, and the initial moment will be opposite to the z-axis, that is negative. So whether the electron is rotating clockwise or anti-clockwise, the diamagnetic behavior exists in both cases, and the effect of the field would then be to speed up the electron, resulting in an even more negative moment, that is, the induced moment would again be negative, diamagnetic, and given by equation 9.27. Thus, the diamagnetic response of an orbiting electron holds good in general. An effect may be shown to follow directly from the familiar Lenz's law. So this can also be extracted from Lenz's law. When applied to an atom, equation 9.27 requires some modification because the electron orbits around a spherical surface rather than in a circle. Okay, now we know that the electron is in fact covering a spherical surface around the nucleus. It is not just a circle, but it's a spherical spherical motion. So we must keep the other dimensions here. So only the cross section normal to the field is effective in the diamagnetic response, and hence on average we should replace r square in equation 9.27 with the average value for the spherical shape, which is 2/3 r square. Okay, the nu r being the radius of the sphere, and this leads to our modified equation delta mu is equal to minus E square R square over 6 the magnetic susceptibility, given that the atom has Z electrons and that there are n atoms per unit volume. The susceptibility, we have m is equal to nz delta mu for the entire atom, where chi we know is the ratio of m and h, and this comes out to be mu naught m over b, where r square and this chi is minus mu naught E square over 6m into n into z into average value of r square, where r square average is the average square radius of the electron. The averaging is done over all the occupied orbitals in the atom. This expression yields values which are of the same order of magnitude as those obtained by measurements. Thus, for n, this is a typical calculation that is, for n is equal to 10 to the power 29 per cubic meter, z is equal to 10, the atomic number, and average R square is 10 to the power minus 20 meter square, and appropriate value for the constant in 9.29, we find that chi is 10 to the power minus 5. Okay, what we have got here? We have evaluated the value of chi using the basic magnetism, starting from the Lorentz force and the force due to the externally applied magnetic field, and we have obtained chi is equal to 10 to the power minus 5, which is exactly the same range as experimentally observed for diamagnetic solids. So we have been very successful in developing a theory which is inconsistent with our experimental observation, and you should go for table 9.2 and see that this is the table. So here we have seen the diamagnetic substances all having negative magnetic susceptibilities, and the magnitude is of the order of 10 to the power minus 6. So diamagnetic susceptibilities per gram ion for rare gas atoms and for ions of filled shell structures. So diamagnetic susceptibility is observed most clearly in those solids in which the atomic shells are completely filled. Examples of these are provided by rare gas crystals and also ionic crystals, whose magnetic susceptibilities are given in table 9.2. In the case of covalent crystals, which are also diamagnetic, equation 9.29 can be applied only to the core electrons. So this equation 9.29 is in fact the Langevin diamagnetic equation, and this equation is observed by the inner electrons in a covalent crystal which are paired up. And okay, the electrons forming the bond have orbitals which are far from circular, and hence the deviations leading to equation 9.29 does not apply here. The susceptibility of a covalent crystal may be written as chi is equal to chi I plus lambda, where chi I includes the effect of the core electrons and lambda is the effect of the bonding electrons. So for covalent diamagnetic substances, the situation is a bit different. One can determine the value of lambda for a specified bond empirically in a given compound and uses this value in other compounds in which it occurs. So when some of the atomic shells in a solid are incompletely filled, the substance then has a paramagnetic contribution, and this we shall discuss in our next lecture. Okay, thank you very much.